Okay, let's look at how to create an exponential equation from a data table. We're going to find a model to fit this data. So first thing, we're going to look at the ratios between each of the consecutive entries in our data table. Remember that an exponential function means continuous multiplying. So if we're looking to go backwards, we're going to find the ratios of consecutive entries in this data table. So I'm going to take the 1999 population, divide it by the 1998 population, and see what ratio I get. And I get 1.0116. And I'm going to do that for each consecutive pair of years here in our table. And as I continually divide those out, you're going to see that we're pretty close to the same value each and every time. And what that means is that if the ratios of the consecutive years of growth are consistent, then that is indicative that we have exponential growth. So once I know what these ratios are, I can go ahead and build my exponential model. So if we're trying to predict the population in millions in the year 2010, I'm going to build my model. Here, remember, is our basic exponential function form. Y is equal to A is going to be our initial amount, which we know our starting year is 1998, so 276.1 is going to be our A value, times B, that's going to be our growth factor, which we have estimated here to be about 1.01. And then in the year 2010, well, that is from 1998, 2010 is 12 years later. So this is going to be our exponential function. Y is equal to 276.1 times 1.01 to the 12th, which is going to give us about 311.1 million as our population prediction for the year 2010. Okay, so let's see if we can do the same sort of thing using our technology. So here is our data table, which you will find on page 25. This is example 5. So here are years from 1880 to 1990. And again, remember when we're doing regression with our inspires, we need to put in 0, 1, 2, 3, 4, etc. for our years. So we're going to bring up our inspires here. And okay, so here we are with our Inspire. Remember, we need to go to a spreadsheet. And the first thing we need to do is we need to name our list. So we're going to name our first list our X list, and our second list our Y list. And you can see as I've done that, it's automatically going to populate the values for me because I've already entered them. But you're going to enter your X and your Y, and then 0, 1, 2, 3, 4, etc. in the X list, and then the data in the second column in the Y list. So go ahead and pause the video and get all of your data entered in, and then when you're ready to continue with your data, restart the video and we'll go through how to create this regression line. Now we have our data entered into our X lists and our Y lists, so we are now going to generate our regression equation. So we're going to hit Menu and Statistics, Stat Calculations, and we want to go down to Exponential Regression, which is the shortcut for that is A, or you can just scroll down to get Exponential. Our X list, we need to change that to be X, and our Y list, we need to enter Y. And the rest of the default information is okay, so we're going to hit OK. And you can see that's going to generate the things we need to build our regression equation. Here's our A value, so 54.4696, and our B value is 1.15193. And then all of these things are other statistical calculations that we don't really need to be particularly concerned with. So this is going to generate our exponential equation for us, and we're going to go ahead and graph both our data points in a scatter plot, and then we're also going to graph our regression line, and we're going to see how closely our regression equation fits our points. So we're going to go to the home screen. We're going to grab a graph, and then this is in function mode, which we do not want. We want to first graph our scatter plot. So hit menu, graph entry, edit, and we want a scatter plot. And then for x, our x list is conveniently going to be x, and our y list is going to be y. And we're going to enter that, and of course we don't see anything because our data is too large for this viewing window. So we're going to go to menu, we are going to zoom, and we're going to go down to zoom fit, and there you can see there's our data points lining up. And now what we want to do is we want to test out, we want to see how good is our regression equation. So let's hit menu, and then now we want to enter a function. We want to enter our exponential function. And when we do that, this is coming up F3 for me, yours is probably coming up F1. What we want to remember is that our calculator stores that regression equation as the previous function. So mine's coming up as F3, so that means in F2 the calculator has stored my regression equation. So to get to that, I hit tab and up, and right there this should look familiar to you. You should remember that's our A and our B value. So we're going to hit enter, and as we do that we're going to see right here our regression equation very nicely fits over top of our points. So our calculator has done a great job estimating a curve to fit our points, which is what regression is all about. Okay, so let's go back into our PowerPoint here. And there was our data table, and if all goes well, this is a picture from your book of what the data points look like with the regression equation on top of it. And now we're going to try to predict the population for the year 2000. So all we would need to do is put in information to our regression equation for 2000. Well, 2000, our x would be the 12th, because remember we were up to 11. So after 1990, because we're going by decades here, 2000 would be next, so our exponent is going to be the 12th. So f of 12 gives us 308.2 as our estimated population in millions for the year 2000. Okay, so what is the annual rate of growth? Well, this exponential equation is what estimated our population. But if you remember, our periods were decades, 1890, 1900, 1910, etc. So this number, this is telling us we have about a 15% growth over 10 years. But we're looking for what is just 1 year, or an annual rate of growth. So what we need to do is we need to take into account that that 10 years is how we got this 1.1519. So when we added whatever our annual rate of growth was, this r, onto 1, and we raised it to the 10th power, that's what generated the 1.1519. So we're going to go back through and we're going to solve this for r. So we're going to take the 10th root of each side, and then we're going to subtract 1. So the 10th root of 1.1519, and then we're going to subtract 1, is going to give us 0.014, or about 1.4%. So every year the population was growing at about 1.4%. Okay, and the last thing we're going to look at here in our exponential function section is the number e, because if you think back to your pre-calc, we used e a lot with exponential functions, and it appears in a lot of different sort of exponential models that we see. So this is just going to be a quick look at where does e actually come from. This function here actually generates the value that we use for e if we look at x values that are large or small enough. So here's sort of the definition of e. F of x is equal to 1 plus 1 over x to the x power. So if we trace to extreme values for both positive x and negative x, so if you were to type this into your Inspire as your f of x function, this is what your graph would look like. And if you put a tracer on it, eventually as you went out here this way and you got larger and larger and larger for e, or for x, I'm sorry, or if we traced this way and we got smaller and smaller and smaller, you're going to see the y value, it looks like we kind of have a horizontal asymptote here, is this number, 2.718281828, etc. And that is the number that we use as e. So this function right here is where e comes from. If you use very large or very small values of x, this function kind of sort of stops or continuously approaches this number and generates this e value. So exponential functions, e to the x and e to the negative x, we use them all the time in exponential. One example that I'm sure you remember is the compound interest, which was y equals p times e to the rt. Sometimes we call that the PERT formula, but there are other times when we're going to use e in our exponential functions as well. Okay, so that wraps up section 1.3 for us. Here is your homework assignment on pages 26 and 27, 1 to 39, the odds. Questions, please make sure you email me and let me know. I'll be glad to help you out. Okay, we'll see you back in section 1.4.